This is a lesson on the integrated rate law. This is the theory. How you work it in the computer will be given to you later. What you do is use process in calculus called integration to change the V rate law into integrated rate laws. First order reactions look like K times concentration of A. If you integrate that, what you do is you end up with an equation, and actually it's equals negative change in A over delta T. So if you integrate that, what you do is, it's a bit, reverse the orders around, that's okay. Don't worry about that. If you're not in calculus, don't worry about it. What you do is you end up, through the miracle and magic of calculus, you get natural log of A is equal to negative KT plus the natural log of A0, A naught. This is the original amount. So A naught is the concentration of the original amount. Natural log of any amount throughout the time is there. K is a constant, rate law constant, and T is the time, seconds, minutes, whatever it is that you have. This corresponds to Y equals mx plus b. This is your y-intercept. This is the variable that you're looking for. This is the slope, and the independent variable is the time. So if you graph most of the time it's going to be up above here. If you graph, you'll get time and natural log of A. This will be your natural log of A naught, your original amount. The slope is negative, it's going to be descending, and it's going to form a straight line. So this would be a graph of concentration, natural log of the concentration versus time graph. What you do is you plug in data, lab data, into your calculator or graph it. In the olden days, that's what we used to do. But you use your graphing calculator and plug the numbers in, and you get it to work that way. So in class, I'm going to show you how you do that. The half-life, the time it takes for half the stuff to disappear, is equal to 0.69 divided by K. So that's the two equations that you have to do with this. So basically what you do is you plot data, and if your data falls along a line, fairly close to a line of natural log of the concentration, then you can say it's first order. So you tell it's first order if you graph natural log versus time, and if you get a straight line, then that's the equation that you get. Again, we'll show you, this is just a theory behind it, show you how to work the machine, work it on the calculators when we get to class. Second order, negative change in concentration of A over delta T equals K A squared. Do the magic of integration. and you end up with 1 over the concentration of A, not natural log anymore, equals a positive KT plus 1 over the concentration of A naught, the original concentration. Again, this corresponds to Y equals mx plus b. Notice that the slope is positive, and these slopes do look like this. Here's your time, and here's your graph of 1 over concentration, and your graph looks like this. So if you plot data and they fit, line of best fit gives you a fairly straight line when you do this, then you can say it is a second order equation. And if it's a second order equation, you can plot the original data in, and one of the things in the time, and you can calculate what K is. Again, this is on the graphing calculator, fairly easy to do, but we'll get to that in class. The half-life equation, time for half the stuff to disappear, 1 over K times the concentration of the original amount. What you do is you pick half of A is some certain number, and half of that goes here, and you go ahead and solve for T, and that's what equation you get. The last one is zero order. Negative change in concentration over time is equal to K. And if you integrate that, you get concentration of A is equal to negative KT plus concentration of A naught, Y equals mx plus b. And in this case, most of the time, the T is on the bottom, or towards the bottom. So this is the concentration. This is T. And if you graph that, it's a negative slope, and it goes down like that. Again, use your graphing calculator. If your data falls on the line of best fit, you get a straight line graphing the concentration of A versus T, you have success. The half-life equation, concentration of A naught divided by 2K. Again, that's, say your original concentration was 1 molar, then you put 0.5 in and solve for T, and that's how you work that. If you have multiple reactants, as is the case, you treat one at a time, just like before. And in this situation, say you have A plus B yields C. When you do this, you'll vary A, but you'll keep this very large. If you want to study A, this would be huge. Huge, if I could spell it, would be dangerous. H-U-G-E. This would be a huge number, so that the change in count of B would still be the same amount as A, but the difference in the concentration, if you go 1 molar or 2 molar minus 0.1, it's about 1.9. Here, if you have 0.2 molar minus 0.1 molar, it's half as big. So the change in A is noticeable. B while it does have some effect, it's, again, such a large number that the amount of change doesn't matter. And if you do even smaller than 0.1, say 0.01, the effect is less than 1%, and you can ignore it. Here, as it decreases more and more, it's going to be more and more different than that. That concludes this lesson on the theory behind integrated rate laws. When we go over to class, we'll talk about how you can do this on your graphing calculators.